Okay, grade 11s, here is the second example of the stoichiometric calculations. And we are not yet looking at limiting reagents, but we will do that soon. Okay, so for now, this is on page 192 in your textbook. Example 2. When iron ore containing iron oxide is reduced by carbon monoxide in a blast furnace, iron and carbon dioxide are formed. Write down the balanced equation of the reaction. So that's in any case always the first step that you do. So we have iron oxide being reduced through carbon monoxide, and they tell us that iron is formed and carbon dioxide. Okay, so tell us that this is what's being formed. Balanced reaction. So now we take through steps. We've got 2 irons, 1 iron there, so we need a 2 there. And then we've got 3 oxygens here. We've got 3 oxygens over here. Okay. We've got 4 oxygens and only 2 over here. So we're going to need a second carbon there. Let's see if it works. So that means 4 oxygen, but now we've got 2 carbons, so that means we're going to need a 2 over here. Which makes us a little bit different, right? So we've got 3 plus 2 is equal to 5, and we know it has to be an even number. So my suggestion would be to make this to a 3. Then we've got 3 times plus 3 is 6, so we need 6 oxygens over here, which we need a 3 over there in any case because of the carbon. And then it is balanced. Okay, 2 iron, 2 iron. 6 oxygens, 3 carbon, 3 carbon. So that is balanced, and that is the first question. The second question, calculate the mass of iron produced from 100 tons of iron oxide. So can you see now what's taking place here? We are getting on to the train. We have information here. 100 tons. That is a lot. Sorry, 1,000 tons. Okay, so it's 1,000,000 kilograms. Can you see it does not make sense to work in moles now? We are going to work in kilomoles at least. Okay, so we need to move onto this reaction in the sense that we are going to use our molar mass to do that. Then we are going to use the molar ratio to get to iron. For each mole of iron oxide, 2 moles of iron will be produced. And then we're going to use the molar mass yet again to get to the amount of iron produced. Okay. So, first step, calculate the molar mass of iron oxide. Okay, so molar mass of iron oxide, and we've done this with example 1 as well. So it's 2 times 55.8 plus 3 times 16, and then we get 159.6 grams per mole. Okay, that then means that 1,000 tons, so we want mole, so it will be mass divided by molar mass, and I'm going to put 1,000,000 kilograms divided by 159.6, and then we will get 6,265.66 kilogram. Kilomole. That means 1,000 mole. Okay, so that's part of question B now. We want to know how much mass of iron is produced. Okay, so this means 6,265 kilomoles of iron oxide will produce double the amount of moles of iron. So we are going to times by 2. then you can say therefore 2 times 6265,66 kilomole iron is produced, which is 12,531,3. Well, this is 633. It's going to be 32. So let's just stick with that. I did not round off when I did this calculation. Okay. Now we have to go from, to look at the reaction again, from moles to grams, or kilomoles to kilogram. Okay. So we are going to use the molar mass of iron, which is 55.8. So now we just say molar mass of iron is 55.8 grams per mole. Therefore, mass is equal to mole times molecular mass. So 12,531,33 times 55.8. And that will give us 248,000 kilograms. Okay. So if we want to take that to tons, it's 699 tons. And that was question B. Okay, let's look at number C. C asks, calculate how many tons of iron oxide are needed to produce 1 ton of iron. Okay, there's a few ways to calculate this, but we have already done calculations where we know that 1,000 tons of iron oxide produces 699 tons of iron. Okay, so the only thing we need to do is to say, okay, I'm just going to write this down. 1,000 tons produces 699 tons of iron, right? So now, if we want to know a 1 ton iron, how many tons of iron oxide? That's what we want to know, right? So the only thing we need to do is we need to work with the ratio. So you take your answer, like 699 correlates with 1,000. So that means 1 ton will be 1,000 divided by 699. And that is the quickest way to do this calculation. So then you say, therefore, 1,000 divided by 699 is 1,43 tons iron oxide is needed. So that's the quickest way to do it. If we did not have this, okay, let me explain how you would have done it then. You would have put in 1,000, the mass of 1,000, right, over here. You would have divided by its molar mass of 55.8, then you get the amount of moles. You take the amount of moles divided by 2 to get to the amount of moles of iron oxide. Then you take the amount of moles of iron oxide and you multiply with the molar mass to get to mass. Can you see? Get onto the train, go to the next station, get off. That's basically your strategy every time. Okay, let's look at the next question. The next question is question D, and they ask us, if the iron ore contains 85% of iron oxide, calculate how many tons of ore are needed to produce 1 ton of iron. So now we are back at some of the information that was asked for question C, right? So we know that, this is now for D, 1,43 tons of iron oxide gives us 1 ton of iron, right? But now they want to know if the ore is 85% iron oxide. How many tons of ore is needed to produce 1 ton of iron? So what we need to do is we need to understand that 85% of the ore is iron oxide. That means 1.43 tons only represents 85%. So 1.43 is representative of 85%. So if we want the complete number, we have to divide by 85% to get to the total amount of ore, right? So then we say 1.43 divided by 0.85. And that will give you a final answer of 1.68 tons of ore. So 1.68 tons of ore, 85% of this is 1.43 tons of iron oxide. And 1.43 tons of iron oxide produces 1 ton of iron. So please understand how to look at this. We work with the conservation of mass, and we work with this whole concept of changing everything into moles and then working with the molar ratio and then changing back into whatever is needed, mass or volume. Hope this helps.